We've talked a lot about laws of physics and how they're inconvenient for hardware people and thus inconvenient for software people. But you know, one thing about laws, almost all laws have loopholes, okay? And the laws of physics are no exception. There are some loopholes we can take advantage of in some cases. Unfortunately, like loopholes in normal legal laws, there are limits to these loopholes, but still, they are loopholes and we should take advantage of them, full advantage of them wherever we can. So let's go through some of them. One really cool one that I've taken shameless advantage of over a period of more than 25 years is the fact that read-only data is replicated in all the caches. So if a whole pile of different CPUs read the same data, that data gets pulled into all those CPUs' caches. And that means all the CPUs have high-speed access to that data. And we show that here. We've got the little black squares that are in that little green area, the same variable just everywhere. And so all the CPUs can get access to that. And of course, that may seem kind of strange, especially if you're as old as I am. I mean, I grew up in a time when we had this thing called Unix, as before Linux, and we ran it on one of these really fancy PDP-11s. The thing was, you had to configure by hand your kernel to exactly what hardware you had. Exactly, okay? And that meant that if you didn't compile in the fact it had a floppy drive, you couldn't access your floppy drive and then maybe your system wouldn't boot even. You had to compile into the kernel where the swap partition was. And there were in fact, you had to get 3 different places in the kernel correct as to where the swap partition was, otherwise it would do interesting things. I know that because I only found 2 of them once. And in fact, if you forgot to mount the floppy drive and you tried to use the floppy drive, that was a kernel panic, which usually irritated everybody else who was trying to use the machine at the time. I know that because I did that too. Well, things have changed. What happens now, you got a laptop, you slam a memory stick into it and, oh, memory stick's here. You can offline CPUs if you're using Linux, probably Windows 2, I don't know. You can connect to the network or disconnect to the network. Stuff can like appear and disappear and the system just notice it. It's amazing what you can do if you have more than 64K of address space, all right? But what this means is there's a lot more data that almost never changes. There's a bunch of data that keeps track of what hardware you have because the kernel is built just to take whatever shows up, mostly. And so it has to keep track of what do I really have versus what I might have. And that could change at any time. You could throw a memory stick into it or pull a memory stick out anytime you wanted, but you don't do that very often. And so that data, if you were really heavily using your I/O, would tend to be replicated in the caches, and your access to those data structures describing what the system had and didn't have would be quite fast. So what's happened is that larger memory has changed the way that the machines actually operate. There's much more data lying around in the system describing what's there, whereas in the old days that was all code that was either there or not compiled in. You had to very carefully select what you had. Life's much better this way than it was then, believe me. Okay, and in real estate, of course, the 3 most important things are location, location, location. And in parallel computing, it's very similar. Locality, locality, locality. If you can make it so that you split your problem up nicely so that the data can be local to a given CPU, a given socket, a given system, your life is going to be much better. Things are going to go much faster. Okay, one question is, well, geez, we got all this hardware, we got all these transistors. Can't the hardware help us? And in fact, it does quite a bit. And these are just 5 of the larger big animal optimizations it does. Big caches, of course, is a very popular thing. You've seen these things grow from small numbers of kilobytes to many, many tens of megabytes these days. We'll talk about store buffers, speculative execution. Big cache lines are kind of a 2-edged sword. In fact, a lot of these, optimization in general, it's kind of a 2-edged sword. And we'll see that some of these are too. Cache prefetching is another one that can be very good or very bad. All right, so the good thing about big cache lines. So you got CPU 0, he wants to read variable A. Well, variable A happens to be in a cache line down there in the bottom. It's got A, B, C, and D in it. That's at CPU 1 right now, because maybe CPU 1 was the last one to write to it. So CPU 0 says, hey, I want to read A, give me the cache line. And then that's the arrow coming down. So that's why remember we had over and back speed of light? Well, that's the over part. And then CPU 1 says, oh yeah, cache line, okay, here it is. and that's the back part. So there's this big delay, this long latency between the time that CPU 0 says, hey, I want to read the value of A, and the request goes out for the cache line containing A, and that cache line comes back, and now once it's back there, CPU 0 actually can read A. The cool thing is if CPU 0 was next going to read B, C, and D, do it right now. Just, that's right there, you've got it. Almost no additional latency to get the rest of the data in that cache line. So having a really big cache line would mean you could just get all sorts of data. You pay the price once. That speed of light's going to get you once. But once you've paid that price, you get your money's worth of the rest of the data in the cache line. Well, that's the good side. There's also a bad and ugly side. Now, it could be that we've got A, B, and C in there, and CPU 0 wants to write to A, and CPU 1 wants to write to D. Well, they're both in the same cache line. And so that cache line is going to go pinging back and forth between those two CPUs. And this is called false sharing. How many people have heard of false sharing or like run into it? How many people have had to beat their head against the wall to figure out what the heck was being false shared and fix it? Yeah, you know what I'm talking about. And the bigger you make your cache lines, the more likely you're going to end up with a situation where several CPUs are fighting over the same cache line because they want to modify it at the same time. All right, so it's an optimization. It's the same as our software optimizations. You know, you use a hash table, that's fast. On the other hand, you don't get to do range searches anymore. It's the same kind of trade-off they're facing that we're facing in software all the time. All right, so big cache lines, they can help, they can hurt, but they're getting larger. Alignment directives are what we do to get around that. So what we could do here is we might use alignment directives to make sure that A and B are on one cache line and C and D are on another. Once we've done that, well, CPU 0 still takes a long latency to get that cache line from CPU 1 to begin with. But once that's happened, it can write to A all it likes. It's just right there. Likewise, CPU 1 has C and D, and it can do whatever it wants there as well. So the big way to get around false sharing, is the alignment. Okay, well, that's really nice. We've also got prefetching, which can also be really good. It was good when we picked up A and got B and C and D for free. If we have prefetching, we can still have the two cache lines and maybe have them with different CPUs, but we can also, if they're both in the same place and it's clear the other guy is going sequentially, we can send both of them at once. We kind of cheat the speed of light with a second cache line because we anticipate that the other CPU is going to need it. And so then it reads A and then waits for A to show up, and then it gets to read all of B through F like that because the prefetching happened. And that's wonderful, except that it's got the same downside. If no matter how, now don't get me wrong, hardware these days has really, really clever prefetching heuristics. And they would generally avoid this sort of thing. But you show me hardware with whatever heuristics, and I'll show you software that will break those heuristics. Okay? I mean, that's the way of life. You win by the heuristic, you lose by the heuristic. And you can end up with this sort of thing where they fight for a little bit over the, you prefetch it, but you shouldn't have sent the second one over because he's not going to go to it, and you need it back where you were start from, and you can take an extra latency because of that prefetching. So it's an optimization again. It can work very well in some cases. It can hurt in others. Store buffers. Well, one of the problems, if you just did a store and you didn't have a store buffer, you would try to do the store, you'd have to wait for the cache line to come to you. In this case, the cache line's on CPU 1 and would have to get to CPU 0. And you'd have to wait that time. What a store buffer allows you to do is say, okay, we're going to store this, so we'll just record the address and the value in my little store buffer locally. We'll ask for the cache line. It'll get here sometime or another. And when it gets here, then we'll do the store. And the cool thing about that is the CPU can proceed with its other operations while the store is pending. And some machines have really big store buffers, many thousands of entries. In fact, on some machines, they call it the level 0 cache. It's really a giant store buffer, okay? Depending on, some machines it's that way, some it isn't. But there are some machines where they call the level 0 cache is really a huge store buffer. And that's really nice. But as you might expect from the previous several slides, this is only half the story. This is a big source of memory misordering, and why we have to have these memory models and everything else. Because let's suppose that CPU 0 writes A, 42, it gets stuck in the store buffer, and then it goes and it does a bunch of stuff and it reads A. Well, CPU 0 says, oh yeah, well I've got that in the store buffer right here, it's 42. I just wrote it. And so as far as it's concerned, it wrote 42 to A before it read from, say, E. Okay? The other CPUs, though, they don't see that right until the cache line gets there and gets back to them. So there's going to be a disagreement about whether the store to A or the read to E happened first. CPU 0 knows it stored to A first and then it read E. But there's no evidence of that store going to any other part of the system until much later. And that means the other CPUs think that A happened after E. Okay? And this is even the tightly coupled systems like, tight memory models like x86 or the mainframe or SPARC or any of the other ones that are TSO, they do this because they have store buffers, because the store buffer optimization, allowing the system to proceed, allowing the CPU to proceed with these pending stores is so valuable they can't do without it. Okay, well, what this means is we have to use ordering directives. In C11, of course, these are the memory order, you just get sequential consistent by default, and you have memory order acquire, memory order release, memory order acrel, memory order consume, and memory order relaxed. Although relaxed isn't going to help you much here. It's not going to do much ordering for you. Okay. And so what's happening, this is one of the cool things about the C++ memory model, is it's allowing for pretty much the first time, you could argue Java got there first, okay? But it was only sequentially consistent early on. It added the weaker options after C11 did. The really cool thing about C11 memory models, it allows portability for ordering and pretty good performance for it. I mean, you might be able to write tightly coded assembly and get a little bit better, but in many situations, just using the straight things, I think Fedor will be talking about that later. But it allows us to do that. And what we have is we have the hardware, which is often very different. ARM, PowerPC, Itanium, MIPS, x86, mainframe, and so on have very different hardware memory models. We have a tool chain on top of them, and that tool chain is responsible for providing the C11, C14, C17 memory model. And so it provides a unified view of all of that hardware. And that allows us to do some of these ordering things in a portable manner and not lose that much performance. In some cases, maybe none. Maybe lose no performance. Okay, so last thing we'll talk about is big cache and speculative execution. Big caches actually work pretty well. It's hard to find fault with them unless you happen to be one of these people that are using a battery-powered system, in which case the bigger your cache, the shorter your battery lifetime, up to a point. But even so, the people doing those things have gotten very clever about turning the caches off when the system's not being used. So it helps a lot. You have the bigger the cache, the more data fits in the cache, the closer it is to the CPU, and life is better. However, if you have bigger caches, usually you have to have a taller cache hierarchy. The bigger the cache, the more time it takes to figure out which element of the cache you want. And so that's why we have this L0, L1, L2, L3 sort of a thing. And of course that means you have to check more levels of cache as you're trying to figure out whether the thing is in a cache, and your cache miss latency can get larger. So it's an optimization, there are trade-offs, but it generally works pretty well. Speculative execution is also, it can hide latencies, and we'll see an example here in a bit. But the trick is that one thing you could do is every time you see some kind of ordering directive, the CPU can say, okay, I'm going to wait until I know the stuff I did before is visible everywhere, and only then will I go ahead. Well, that might have been a successful strategy in 1990. But if you're a hardware player today, that's probably not a winning play. What they tend to do is go ahead and execute anyway, and then if they see evidence that somebody saw or had the potential to see something backwards, they cancel the speculation and start over more carefully. Now, what that means is that in many cases you can hide the latency you would otherwise see from directives required to enforce memory ordering. The downside is that you have worst case latency, because you may have to do work, cancel it, and do the work again, possibly multiple times. And also, doing that work multiple times is going to give you poorer energy efficiency. And so again, the battery-powered people would be perhaps less aggressive about this sort of thing. Here's an example. I hope it's visible in the back there. This is a standard message passing type of a thing. You've probably seen it before. So we have a data and a flag. We set the data to a value, and we set the flag to 1 to say the data is available. And we have memory order release there to say, make sure that the flag happens after all the stuff before it. On the other side, we have a while loop. Usually you wouldn't spin waiting for the data, but let's keep it simple. So while the flag is not set, we sit there waiting. Once the flag is set, we pick up the data. We use a memory order require for the flag load, and therefore the data is fetched after the flag is read, which means we get 42. We get the value stored in the data reliably. If we left those directives off, we made them both be relaxed. You can actually, there are tool sets that allow you to run that on the machine and see what happens. On an x86, it won't work too badly. On other systems, you will see things get out of order, and you'll see the flag being 1 and the data being the pre-initialization garbage that was in it before. Thing is, though, if the system is aware, if both the cache lines, both flag and data, are sitting on the first CPU, and it knows they're there and knows nobody else has access to them, it can do those stores in any order it wants, because nobody can see the intermediate state unless it lets them. Okay? Similarly, on the other side, if both the cache lines are sitting there and it knows that nobody else has access to them, again, it can do the reads in any order it wants, and because nobody else can be changing it because it's got the only copy. So the hardware can look into the cache clearance protocol, the protocol used to keep the values constant to convey the memory model across the machine, and can determine when it's safe to cheat, do things out of order. And if it senses a condition that might allow the software to see something bad, it can cancel the speculation and start over. A lot of people get kind of annoyed at me because I tell them the compiler can't do something without messing me up as a parallel programmer, and they say, well, the hardware does it. Well, the reason the hardware gets away with it is because the hardware has a lot more visibility into the state of the machine and can sense when something's going bad and can pull itself back out. If you've got a compiler that can do that too, okay, great, but until you do, there are some things the hardware can get away with you can't. Okay, we'll take a look at maligned workhorse locking. This is kind of leading into some things, just some simple things to lead into Magid's presentation a little bit. This is a stupidly simple lock acquisition, but it's one that has been used in production. You just do an exchange with a, and I apologize for the C, but I managed to fix it on a previous slide, but didn't notice this one. I'm after all a C programmer, working the Linux kernel. So we spin waiting for the value to be not to be 0. The basic idea is the lock word starts out being 0. That means nobody holds it. You do an exchange, you take whatever is there and put a 1 there. If there was already a 1 there, you get a 1 back, you know somebody already held it, so you do it again. If you get back a 0, that means that nobody held the lock and now you hold it, and the value is 1. The release is pretty straightforward. You do an atomic store memory order release of the 0 to set it back. And this can implement a lock, although it has really, really, really terrible high contention behavior. If you do this, if you implement your lock this way, it's on you to make sure you have almost no lock contention, because if you do have lock contention, it's going to hurt. But still, this is something you can do. We can make something a little smarter by, instead of, the problem was we were doing an exchange over and over and over again, so we were just batting the cache line around for all the CPUs, and even so if some guy gets the lock and tries to release it, it's probably somewhere else and it's hard. What we can do is we can just do a while loop and just say, essentially spin waiting, and only once we see that it's released, then we try to do it. And I think I haven't got those whiles nested right, but I'll fix that later. So what we're doing is, instead of doing read modify write on the cache line each time, we're spinning waiting for the value to change. And then once we see we have a chance of getting it, then and only then do we do the atomic read modify write operation that yanks it out of everybody else's cache line and tries to acquire it. This is still suboptimal though. And an example of where it can go bad, thing is that you lock it, they see it's locked, and CPU 1 sees that it's held as well. So CPU 1, that should be CPU 2, sorry. The thing is, the CPU1 knows it can't lock it, but it's got a read copy of the cache line. That means that CPU0 can't release it until it gets exclusive ownership of the cache line, because you don't want the same variable to have multiple values in different parts of the machine, usually. Not with atomic instructions. It'd be okay with stores. They could have to store in different store buffers. That'd be all right. But this is atomic read, modify, write, and it's supposed to look atomic, so everybody has to agree on the value. Now, what happens is that when somebody does unlock, there's a whole bunch of bus traffic that has to happen for the cache line to get yanked out from the readers and get sent to the guy that wants to release it so the readers can actually get it. One way to fix this is use queued locks. And the idea is that you actually make a queue. I'm not going to go through the code in detail. We don't have time for that. There's a paper, a URL on there. These slides will be posted. You can look at it with the kind of the fundamental paper on MCS locks. But the idea is you make a queue out of these things. So that we've got CPU0 holding the lock. So we got 3 states and 2 transitions between them. CPU0 holds the lock. CPU1 is spinning on its own little node there. And CPU2 is spinning on its node. So when it comes time to release the lock, CPU0 has to fight only with CPU1, not all the CPUs. Of course, there's only 3 CPUs, so you're saying, so what? I have had problems on systems of 4,096 CPUs, and believe me, if you have 4,095 CPUs fighting with you, you're in a world of hurt. And so things like this can make it work better. And then once it hands it off, CPU1 holds the lock, and then it hands off CPU2. And again, you have most 2 CPUs contending for a given location, and life is a lot easier in the high contention realm. You know, except that there's one thing that's even better, and that's not to have high contention. The queued locks usually have a little bit more overhead in being set up. You have to do a little more operation, and that costs you in the low contention case. If you can make your algorithms just have low contention, you're in a lot better position. In addition, just spinning all the time may not be what you want, especially in user space code. In the kernel, I can get away with it because I've got a hold of the CPU and it's not going anywhere. In user space code, you can get blocked while you're spinning. You can guide holding the lock and get blocked, and horrible things can happen. So you really would like an adaptive spin sleep strategy. I could probably, this is one of the things about throwing away the slides. I could talk about this for a long time. But one thing you do is have your algorithm use futex system calls in the Linux kernel. Other systems have similar things, in order to spin for a little bit and then go to sleep, so that if it's available right now, you get it, or it's available soon, you get it. If it's going to be a long time, you get out of the way of the people that have it. Okay, reader-writer locking. You know, it sounds wonderful. Read-side parallelism, you know, if you have read mostly stuff, use a reader-writer lock, and life is wonderful, right? So what you normally have for these things, there's been a huge amount of ink spilled on how you can make different kinds of reader-writer locks. This is just kind of a canonical single variable thing. There's a bunch of variations on this. The flag bits may have all sorts of things in them. But you have some number of readers, you have some number of writers, you have some flag bits for fairness. If you want to read, you at the very least have to say you're there. You have to increment the number of readers in the word. And because you have multiple people doing this needs to be a read, modify, write instruction that manipulates it one way or another. Might be compare and swap, might be atomic fetch and add or something like that. And the problem here is that the readers are having to write to memory, write to contended memory, in order to announce their presence. And so you end up with something like that. Every time you go get the read lock, you get a cache miss. Now, if you remember from a slide way earlier, cache misses from one socket to another are way worse than 2 orders of magnitude more expensive than just a normal operation. And so unless you have really, really big read-side critical sections with thousands of instructions in them, you're taking a lot of overhead. In fact, it's likely that you might as well use a exclusive lock, because by the time you acquire and release the lock and do something, you aren't actually overlapping with anybody else's critical section, because the critical sections are short, the acquisition and the release of the lock are long. So one thing we can do is what it comes down to, the key thing here. We mentioned that the hardware people are up against the laws of physics, and that means they need a little bit of help from the hardware. There's a bunch of ways of doing this. I'm just going to give one fairly simple one, and that's a thread local storage variant of a reader-writer lock. What we do is we give each thread its own lock. So you do a read lock by acquiring your thread's lock, and only your thread's lock, and you release it by releasing that lock. So if everybody's reading, they're acquiring each their own locks, their lock remains in their cache, and they get fast access to acquiring and releasing that lock. Yeah, there's memory barrier overhead, there's atomic instruction overhead, but you don't have cache misses. Of course, this is like any other optimization. For this to work, the writing threads have to acquire all the locks for all the threads, and then release all the locks for all the threads. So it made things very nice for the readers, and too bad for those poor writers. And this is kind of a picture of what's happening. Instead of having these big cache miss explosions like we had on the slide a couple times ago, each CPU is just looking at its own cache, and things can go very fast. Again, what we've got is we've got something that is a reader's writer lock that works very well for the readers, but we've lost a little bit of generality because the writers get such horrible performance, especially if you have large numbers of threads. And that, by the way, is one of the reasons that Mag and Michael came up with hazard pointers and I came up with RCU to deal with that situation. But that's another presentation, and we've given those before. At this point, it's time for me to hand off to Magid, and he's going to give us a single producer, single consumer buffer. Thank you. Oh, okay. Let go of that, and all right.
I selected really a simple data structure with very simple interface to be able to dive deep into how we design it, how we deal with the trade-offs between performance, complexity, and generality, and to apply the concepts and techniques that Michael and Paul spoke about, and complement some of the issues that were not covered. So basically, it's a single producer, single consumer buffer is for communication between a single producer and single consumer. It's a buffer with a bounded size, and this is the interface that we want to provide, at least for now. I'll get to blocking later. So this is a non-blocking interface. The simplest implementation would be a single lock. So there is one lock that each of the operations has to acquire and to operate in the data structure using just the sequential algorithm that you'd expect in if the thread is just operating by itself on the data structure. The problem with, so this is what it looks like. You have the buffer and the pointers, but then you have the lock. That's the only thing that is allowing concurrency. The problem with this is that there is no parallelism. Like the producer cannot operate with concurrently in parallel with the consumer. Another problem is that the block itself, whatever implementation, like for example what Paul showed, both threads will be writing to it back and forth, and the cache line will keep bouncing because they're both writing to it. Actually, it's enough that one of them is writing, but they're both writing. Another problem is that it's a lock acquisition requires either a read, modify, write instruction or a fence. Practically, it is read, modify, write atomic instruction. So that's the least of the problems, but it is still like an order of magnitude slower than regular loads and stores. So these are the problems with that single lock and the measure. So I ran that, and the measurements on my machine with on a single socket with 2.2 gigahertz is like 4.3 million handoffs per second. So hopefully we can do better than this. Of course, this solution is very general. Like you're just using standard language, nothing not portable at all. Now we get to Lamport algorithm, the classic single producer, single consumer algorithm. Instead of the lock, it is dealing with it is dealing with these kind of atomic variables, and has all these loads and stores to it that can go concurrent in parallel, and this what gives us the safety of this this structure. Yeah, and so let's look at what are the features that we get from this. What we get is like, okay, we lost the lock. We don't have the lock anymore, which is with all the negative things about it, especially a single lock. It's not fine-grained locking. It's actually coarse-grained locking with all the negative things about it. So we'll see from this that there is parallelism. There's nothing really prevents the producer and consumer from proceeding in parallel. That's good. The other thing, let's look at all these load and store operations. They are load acquire and store release. These are like quite cheap on x86 and not as expensive as full fences on x86 and other platforms. But there's a caveat. I mean, these instructions are, yeah, they are fast, but only if the cache, if you have good cache locality. The problem here is that we have cache line bouncing, and that's because we have data that is being written by one thread and read by the other thread, and vice versa. So this is the downside of Lamport's algorithm. But it is much better. We have, as I said, there's parallelism, and we're avoiding the atomic read, modify, write instructions. So what we get in performance, we improved a bit. Let's see if we can get better performance at the cost of more complexity and less generality. So there's the algorithm by Giacomoni et al. From 2008, and basically they switch things. So instead of the pointers being atomic, they made the pointers like, you know, they're private. But instead, the buffer itself, the items in the buffer itself, each is atomic. And in this example, just to simplify things, I made it like a pointer. But it's actually, you know, it's quite easy to change it to general data with a flag, like what Paul showed. So the features here, we do have parallelism. We didn't lose that. We have fast instructions, as you can see. The load and store are, you know, acquire and release. And we have no cache line bouncing, because you look at the producer is only dealing with the tail pointer, and the consumer is dealing with is managing the head pointer. So there's no cache line bouncing. Another thing is that we have we have improved full sharing, less full sharing, and that's because, the price we pay here is like we have to do something kind of more less general, of like aligning the data to cache lines to avoid false sharing. Without that, we do lose performance. So let's look at the performance results that we get. If we didn't do the alignment, actually we do worse than Lamport, because the head and tail, even though they are managed separately, they are actually, if they are in the same cache line, there will be false sharing, and the cache line will keep bouncing. So by aligning them separately to avoid false sharing, we were able to double the performance of Lamport. So the lessons we learned from this is that we can achieve high performance at the cost of higher complexity and reduced generality. And we looked at how cache locality, false sharing, alignment, these kind of issues. Now let's switch gears and look at what if we want to. So far that was non-blocking. Like basically, the consumer had to be spinning, even if it is doing some kind of like less expensive, like pausing or thing, but it's still consuming CPU cycles to await items produced by the producer. So not all applications can utilize that, and some might need to have blocking consumer. So we'll look at this, and the first thing we'll look is like, okay, we'll use a single lock with condition variables, with a condition variable. So this is kind of like the straightforward solution, and we added a condition variable, but then the problem with this is that we have to notify a quite expensive step that is in the critical path of the producer. So that's the downside, and the performance is quite bad. It's because of the single lock, is the non-blocking implementation is quite expensive. It doesn't look as but it is worse. Let's look at so let's do something kind of more complex with Futex, and so now we're losing generality. It's not something that is available in every system, and it's not like language supported. So let's apply it to Giacomoni. I mean, I already applied it to Lamport, but I'm not going to show that. So the difference here is that we added a flag or atomic variable to the items in the buffer, and every in-queue operation, it will wake up the consumer in case it is asleep. It doesn't know, and the state is just like it's either empty or full. So as we see here, that the steps are similar to like the non-blocking, but then what is added is that now the producer will wake up the consumer. The consumer doesn't necessarily always go to sleep. It's only when needed it will. So it's not in the critical path. So let's look at the performance here, and I applied it to Lamport, and it is slightly better than the condition variable, and Giacomoni is it is really slightly better, but really not that much. Let's apply something a little bit more complicated, but we want to avoid this very expensive step of waking up the consumer from the critical path. So for this, we changed the algorithm to use 3 values instead of 2, and it's conditional. So the variable is being set by both the producer and consumer, and so as I'll show, these are a little bit more expensive, or complex. But then the wake up is only conditional. It's being being selective when to wake up the consumer. So that will be a good advantage. There's a slight disadvantage here because both of them both the producer and the consumer might be actually updating the state concurrently. Then we need to have a read, modify, write operation. So this will limit the gains that we can get. And it is in the critical path. So we have compare exchange operation that the producer has to do every time, just to make sure that it didn't miss that whether the consumer went to sleep or didn't go to sleep or not. Let's look at the algorithm for the consumer. It's doing everything, and only when after it gives up and it doesn't want to wait, it will block. But it doesn't just go straight to wait. It has to actually make sure that the state is set using a read, modify, write operation in case there is kind of a race condition with the producer. Again, this is not in the critical path, so it really doesn't affect performance that much. Now let's look at how the performance is affected. Lamport, I didn't show the code here, but Lamport basically, because it's a centralized, the synchronization is done on centralized variables, it actually doesn't really scale or improve that much. But Giacomoni, because we're doing this synchronization on every item in the buffer, we're actually able to achieve much better scalability. That being said, it also shows us that how the choice of being, like if someone says, do you want to have blocking supported or not, it's actually you have to be really careful. We're losing 4x performance just for the possibility of blocking. Even without using blocking, just for the possibility that the consumer might want to block, we are losing that much. So actually, if you're designing a library, or you should provide both, because it's like some user might actually have a very streamlined communication between the producer and consumer, and actually want the consumer to be awake. They can afford to have the consumer to be awake all the time, and the stream of communication between the two threads is actually keeping the consumer occupied. So that's another lesson here. And to summarize what we went through in this talk, so Michael discussed the landscape of parallel programming and how it is changing and how it's becoming easier, but not quite easy yet, and the challenges. And Paul discussed the hardware and software issues that still remain and how they improved and how they interact. And I went through this example that hopefully demonstrated what some of the concepts that we discussed, and demonstrating how these kind of trade-offs can be worked out to balance generality and complexity and performance. And so thank you. And if you have any questions for Paul and Michael and myself. Please. Okay.
We have microphones there and there, I think, if anybody's got questions.
Okay.
Okay.
Yeah,
We have contention on microphones. This is demonstrating load imbalance, just so you know. All right.
Cool. So could you, maybe Maged, could you point to any open source high quality SPSC or NPM queues that you would recommend?
I plan to provide that, so I haven't, yeah.
Right.
So probably soon, yeah.
So hi, Majid. Question for you about the times that you were showing, the performance times. Was that with high contention or low contention, or?
Basically there are two threads. I should say the buffer was like 1,024 items. It was of course, two threads. I limited to one socket because actually we were losing performance on multi-socket. There's no need for that. And it was, basically it's equivalent to the producer giving the consumer a pointer and the consumer kind of depositing somewhere that, and that's it, turning around to get the other item. So it's quite high contention, yes.
Okay, would the relative performance of the different solutions change depending on the degree of contention in your system?
Of course, if let's say there's imbalance between the producer and consumer, then that would be like a different bottleneck. But actually, what you expected from something like this is like the producer and consumer really balanced. Otherwise, there'll be, or either they're balanced or the consumer, I mean, the producer is actually just, has more pauses, and then the consumer would just have to go to sleep, and in that case, would want to use the blocking version. Yeah.
So my question is probably for Paul more. So the question is, we are saying that if we have bigger caches, of course, performance is better because most of the time CPU is waiting for data from the memory. So, and at the same time, the size of the L1, L2, L3 is not changing in recent years. And so if we search the web, it says that it's expensive to build bigger caches. But how much it's expensive? What kind of tests you did at Intel, and what are the prognoses?
Well, for Intel, I have to direct you to somebody who works for Intel. I'm actually working for IBM.
Oh, for IBM, sorry.
But,
or in the market at all?
What I can tell you kind of in general, what they tend to do, they have analytic models, but they also run traces on a bunch of different applications and actually look at, okay, if we had this geometry, what would happen? There's trade-offs. If you, and the upper level caches tend to remain small because people want, what happens is that if you have a physically tagged cache, in other words, what happens, you have a cache line, you have to have the address that the cache line corresponds to in its data. And there's a question, should that address be a virtual address that the user's using, or should it be a physical address that the hardware's using? And there was quite a bit of controversy 30 years ago, 20 to 30 years ago, and the physically tagged people won, pretty much, as far as I can tell. What that means is that if the cache is big enough that you need to use bits that get translated, so if you have a 4K page size, if the cache is big enough that you need some of the bits that are translated, you put the translation on the critical path to that innermost cache, and that really slows things down. And so they tend to keep the close caches small so that they can just grab the lower bits that don't get translated anyway, applies the cache, and be translating the address in parallel. So that's one of the reasons why those top caches tend to remain tiny. They could, of course, have put more, it's kind of like a hash table, a hardware hash table. So you kind of have buckets, and you can have more stuff in the buckets, but they don't do linked lists very well in hardware. And the problem is if you have more stuff in a bucket, you have to have do more comparisons. You have to have bigger fan in and fan out to the gates that are checking the addresses, and that starts hurting your performance and also increasing energy consumption. So those are, I can't give you a really exact answer to it but that's, from a software guy's viewpoint, that's kind of where it is.
Thank you.
Any more questions? Well, if not, you guys have an unfair advantage for break.
Thank you. Thanks, everybody.